So, hi everybody. No, hi. This is the part where you say hi back. Happy Thursday. We ready to talk about some CFA? We started talking about that last time. Here's a picture to jog your memory. What can you tell me about this picture? What's it for?
It's a way to show the connections between the items and latent effects.
The items and the latent effects. Which ones are the items?
The items are the rectangles,
Yes.
squares, and the quote-unquote imaginary things are in the circles.
That's right. So the boxes are for columns in your data set, usually columns, sometimes rows, and the blue circles in particular are meant to indicate latent traits. What's the arrow thingy going into the circles? What's that? Yeah, that's one way to do variance, right? The other is to show an actual separate circle for it. So convention is that it's done this way for errors and then this way for factors, but you'll see exceptions to that as well. What are the red lines?
Those are the factor loadings, or the main effects, or that factor per item.
Yeah, let me do this as a multiple choice question. Does it matter which way the arrows go, yes or no?
Yes.
Yes, remember what I told you before? If you get the arrows backwards?
Tell me you don't know.
Tell me you don't know CFA without telling me you don't know CFA. Yes, the arrows matter. Going the other way is actually a formative measurement model, and we'll talk a little bit about that. So it is a different prediction. Let's see here. Let's see if we can get everybody talking today. I had great success with that with my last class last time, so we're going to do it again. So that means that if you're shy, you should answer one of the first questions because they'll just ramp up in complexity. That's my pro tip for you. What's this stupid triangle thing for? Not that I'm biased. Intercepts. Yeah, this is how we get means and intercepts. So this stupid triangle thing is a column of ones. That's what it is supposed to refer to. So each item is going to have three things estimated: factor loading, error variance, and intercept. One per item is sort of the default. Factor loadings, give me synonyms for those. Or other words that could be applied to describe them. Slope, that's one. So the trait is the predictor. The item response is the outcome, and so the factor loading is a slope. So it tells you what? Like if my factor loading is 2, how would I put that into a sentence? Like this one right here. Let's say this gamma, or not gamma, lambda, there we go. 1, 1 is 2. Zoomers, you can play too. Yeah, I see you, Elizabeth. You got slope. Good.
Tell you how discriminating it is?
Oh, that's one synonym. Yep. Can you put 2 in a sentence, though? No, you can't? You want to phone a friend?
I'm gonna phone a friend.
Okay, who wants to be your friend? You know, I did that in the other class, and the person was like, I'm not your friend. I didn't want to answer that. I was like, whoa. You have friends, right? Zainab wants you to be her friend. You're sitting with her. Yeah, tell me if this loading right here were 2. Put that 2 in a sentence to tell me what it means.
For a slope, I mean, if it increases 2 points, so like the other variables are going to increase 2 points.
Which other variables are good?
Going to the items there, so follow up with the item.
Yep, so this item response is predicted to be higher by 2 points per what?
1 unit change in the factor.
Yeah, 1 unit difference or change in the factor. So it's the slopes are always the change in y for a 1 unit change in x. So the change in y as the item response would be 2 if the factor score increased by 1 unit. And we don't know what units are yet. That's still coming. But just let me assure you there will be units. We will make that happen, like magic. What's error? E. Yeah, residual, leftover. So this idea of residual here goes by a lot of synonyms. You'll hear this a bunch of different ways. Error, residual, some people call these unique factors. Some people call them specific factors. The only thing you can say for sure is that it's not the factor. That's what you can say this is. It's whatever F1 isn't. So you don't know what else could be in there unless you have a chance to actually measure it and observe it. So if this says something that is systematic in addition to error, you would need other items that also tap into whatever that systematic thing is so that you could be able to potentially pull it apart. So like if part of this error is because this item is reverse coded, then you might be able to separately pull out that variance via a different factor for items that are all reverse coded. But if you only have one item that's reverse coded, you can't tell how much of its error is because it doesn't measure the factor or it measures it differently than the other items. So don't let the synonyms fool you. This is just not the factor. And the, yes, got the Zoomers in the chat, the extra stuff. E for extra, I like that. I like that one too. See, the not the factor comes from a reference to a TV show that they made in the early 90s called Dinosaurs. Any of you remember this? I know you're all too young for this. Ask the YouTube when you get out of class about this show. It was the weirdest thing because it was like, it wasn't animated. It was like people in dinosaur costumes. I know, it sounds bizarre, but they had this thing where the baby used to say, "Mama," and then when the dad would come in, he'd say, "Not the mama." And that's how he said it, "Not the mama." And so that's what I think of. It's like factor, not the factor. I don't know what this is. It's just not the factor. And E is not the model parameter. The variance across subjects in the errors is. So that's one thing that can get a little bit tricky. And because I try to keep things straightforward, I'm just using the regular variance symbol for this. I'll give you the more technical notation in a little bit. Yeah. So factor things then. Likewise, F2 is the score for one person, and then it has a variance that's estimated as a model parameter. What's this line down here, or up here? Where my mouse is? What's this convey?
Correlation between factors.
Close. Put it in unstandardized terms. What's an unstandardized correlation? Covariance, yes. Because this is only the correlation if these variances are 1, and they may not necessarily be 1. So this is a covariance. In the standardized solution, it becomes a correlation, but we haven't really talked about that just yet. And then last but not least, factors have means as well as variances. But we can't estimate all the things on this page. We're going to have to nail some of them down to fix them so that the rest become identifiable. Okay, then I said, we're not going to do equations yet. We're going to save that for Thursday. So, any questions so far or things you want me to say again? Variance between two factors, Kelsey? Yes, I will take that. Covariance. The between part implies the co. No, we're good? Ready to keep going? Okay, so that model, the corresponding set of equations look like this. So we have a separate equation predicting each item response as the outcome. And I'm keeping the color so we can start to keep things straight. So the first term here is the intercept. Then we have the factor loading times F1, because in this picture, that's what predicts this response. There is no factor loading from F2 over to 1, 2, or 3. So that's why these are zeroed out right here. So this set of zeros here and here is a choice. That's what makes this model differ from exploratory factor analysis, where every item has a loading on every factor, and you cannot change that. In addition, it has a crazy set of constraints to make it identified, given that that's the fact. So this is the testable part of the model. You are making a statement that F2 does not predict these y's, and F1 does not predict these y's. So this is entirely under your control. If you wanted to say that y1 was a function of F1 and F2, you could do that. It's called a cross-loading if you have an extra loading besides the one that's primary, and that is also something that you can test whether that's needed. So you decide how many factors there are, and that's based on what you think the items are measuring, and you decide which ones predict which items. The default is that all of the parameters are separate, so we're not making any assumptions about the items measuring those factors equally well. Likewise, we're not saying that the error variances have to be the same or the intercepts have to be the same. Everything is estimated separately. These slopes are linear, so that implies a linear relationship between the factor and the item response. So if the slope is 2, then for every unit change in the factor, the predicted outcome goes up by 2. However, what do you think might happen if this model were applied to ordinal data, like a scale of 1 to 5? I can predict a change from an item response of 1 to 3, right, with my slope of 2, and 3 to 5, and then what happens? It's going to predict 7. It's going to predict 9. That problem? Probably. So this is the biggest issue here, is that we're assuming these item responses are truly continuous and unbounded, and most response formats do not work like that. So at best, this is an approximation that is maybe not too wrong, but it's usually not the right model. It's the easiest to estimate, though, and that's one of the reasons why it's still very commonly used. So the intercepts, then, are when whichever factors predicting it are 0 as the expected response. Here is a more condensed way to write this set of 6 equations into a matrix form. So if you wanted to do it that way, we could have a vector of the y's, we would have a vector of the mu's, so I used capital mu for that, a vector of the lambdas, and then I decided to use u for the collection of the f's because f is already capital and it's going to break my system. But if you come to the rest of my coursework in multi-level models, you will learn that factor scores are the same things as random effects, and random effects are used in that notation. So I just decided to do a crossover event here for the classes. You know, like when your favorite TV show has people from the other TV show in it? They do that a lot on like the Law and Order sequence, Grey's Anatomy, and the Fire show that came after it. Like, this is a crossover event that we got here. This is the first semester in a long time in which I'm not talking about U's at all, so I kind of miss them, you know, bringing them back. And then the E's. All right, so this is great, right? I can look at this. This looks like a linear regression equation. I know what to do with the parameters. We're all good. There's only one problem. Do I know what F is? I don't. F is a belief. F is really the variance that's in common of these things. Draw a circle around it and give it a name. So I might think that I've measured whatever tendency, externalizing, aggression, depression, ability. I might think that, but I don't know for sure. So this is latent. So even though this looks like a standard regression model, the way that we're going to focus on what it does, what it predicts, is completely different than what you normally do. What's going on under the hood, behind the scenes, is that we don't need to know what the F's are. If we believe that they are multivariate normal, which is what we have to believe to make this work in most cases, all we need to do is get their means, variances, and covariances. And then those are sufficient statistics to characterize the F's. So we do not need them. What this model is actually for is to create a pattern of how the items relate to each other. So the prediction that we care about is not really Y. The prediction that we care about is the Y covariance matrix. That's what we're trying to come back to. So this model is going to say, I think these items are correlated in this particular pattern. We would expect, based on this, that Y1, 2, and 3 are going to have more of a relationship than Y1 would with Y4, 5, or 6. Like, we would expect pockets of correlation. We would still expect correlations across the pockets, though, because we have the covariance. So this is making a very specific set of predictions about how these items relate to each other. So the goal then is to compare that set of predictions to what's actually in the data and see how close we are. And the extent to which they match is the basis of model fit. So what we're going to focus on is the summary statistics of the items, not the individual separate responses. Their means, their variances, and their covariances. And I note this is a Pearson-style version because when we get into the next unit, that will differ. In IRT and IFA, it's the same principle. The purpose of the model is to recreate the relationships among the items. The only catch is that how those associations are measured is going to differ because they have to differ in categorical data, and because it differs by the type of estimator, whether you're operating on the full contingency table of all possible categories or whether you're operating on a summary of it, a polychoric correlation matrix. So this is a pattern. And as another crossover event, those of you who've had the longitudinal course, remember when we talked about alternative covariance structures? You're like, no, Lisa, I wasn't in that class. A few people were. Vladimir, I'm looking at you, a couple of the Zoomers here. So we had like autoregressive and Topolitz and banded and all these kinds. Factor analysis is a kind. It's literally a choice in proc mixed for how you can ask for a repeated covariance matrix. And I will show that in an example. So this is creating a pattern. So we're not really predicting y with anything because we don't have the latent variable. What we are trying to do is see if the associations among the item responses are recreated sufficiently by our model and that they match the data. Okay, that's a really, really important point. I want to make sure that I hit that as hard as I possibly can because the way that we approach this is very, very different than how we talk about regression models and everything else. Other types of statistics. So let me show you how the pattern gets made. And to do that, I got to introduce a little bit more notation. So first off, means. That's the first thing that needs to be recreated. If our model is right, then it should be able to recreate each of the item means. Fine. How it does that is right here. So I have a vector of item means that is built from the vector of intercepts, one for each item, the loadings, and the factor means. So if my model looks like this, if I expand this into a series of equations, it looks like this. So the mean for y1 is a function of y1's intercept, the loading times the mean of the factor that it loads on, but not the mean of the factor it doesn't load on. And I'm switching across the PowerPoint built-in equations, and this one is from MathType because once you put in a bunch of huge matrix equations, it makes your file really, really big and it takes like 10 minutes to save. So I had to economize in a few spots like this. So this is what the model says should happen to each of your means, and so long as you get a separate intercept for each item, they will usually perfectly recreate the means. So for this reason, it is the most common way to set up your model is to force the factor means to be 0. That way the intercepts become the item means. Okay. So that's how you get the means. It should be right as long as you give each item its own intercept. How it gets the covariances and variances is a little bit different. So this is the most common way of notating a confirmatory factor model in matrices. And so I note that my version of factor variance, variance of f, is that symbol, phi or phi, we can take a vote on that one, and my version of error variance is this one. So if you look at other people's notation, you will see these things instead, and I just deliberately decided I don't like that because I want you to learn as few new symbols as possible. Working memory load needs to be kept to a minimum. That's my belief system. So these are the lowercase versions of these. So sigma is the end result of what we are trying to do here. It's what is getting predicted by the model, is the covariance matrix that looks like this here. So these should all be predicted variances on the diagonal, covariances on the off diagonal. So it's built from the loadings, the factor variances and covariances, and then the loadings transposed. So when you see this, like something, something transpose, think squared. That's what's happening. It ends up being loading squared times the variance of the factor is the part of the item variance due to the factor. We'll see that in written out equations, but just that's when you see that pattern, it's squared. That's what's happening. So this part, the red and the blue here, is the part that's due to the factor, and then the leftover part here, psi, is not the factor variance, the error variances. So then I have each of these written out. So here's my lambda matrix that goes with my two-factor model. Note the patterns of zeros. Here is the variance of my first factor, the variance of my second factor, the covariance between them, and then the same loading matrix pushed over, transpose, and then the error matrix. Now I have a separate error variance for each of my items, and I have zeros everywhere else. That is a choice. We start with that as a default most of the time. But if you believe that the items have something else in common that's not the factor, you can estimate a covariance in any of these spots. Those are called error covariances or residual covariances. That's the most common way to address a model that doesn't fit, is to add extra relationships where they're needed. Okay, so I'm going to just let this sink in for a second here. How we doing? And I'm not going to make you do any matrix multiplications, okay? I'm not. It's not my jam. The computer's going to do it for us. But I want you to see how the patterns get made. This is the end result, okay? So M plus or SAS Cayless or R Levon is going to crank through this, and this is the pattern. I know this is very busy. We're going to take it piece by piece here. So on the diagonal are the variances. So the variance of item 1 is where my mouse is right here. Can you all see that? The variance of item 1 is a function of its loading on the factor that it measures, squared, times the variance of the factor, plus error variance. So what this is saying is that the total variance is partly what's captured by the factor as a function of its loading. So the contribution of the factor variance is amplified if the loading is strong, like we want, and it's diminished if the loading is weak, and then the rest of it's error. Same thing with item 2, 3, 4, 5, 6. The only thing that's different is that each item gets its own error variance, and each item gets its own loading as a weight for how much the factor is contributing to it. Because you're giving each item its own error variance, these will almost always be perfectly reproduced. Because whatever's not covered by the factor, E variance can just become that number. Like it can just plug the hole to get to what the total variance needs to be. Covariances then. Let's take this one right here, between item 1 and 2. The covariance between item 1 and 2 is a function of what they have in common, their latent factor variance, and then each of their loadings. So there are tracing rules. Let me get out of this for a second and go back to the picture. Basically, if you want to know how related items 1 and 2 are, you take this loading, go up here, and take that loading and come back. Same thing if I wanted to know items 1 and 6, I start here, take that, take the covariance, and then take that. So the picture helps to tell you what the pattern is. Go back to this, there we go. So the loading of the first item times the variance of the factor they have in common times the loading of the second item. That creates a number. And then the question is, this is what the model says the covariance is. What is it in the data? How far off are we? And so our indices of model fit, global model fit is like a collection of overall how far off are we. Local model fit is like this one, like how far off is this one. So if you get your pattern back and you get your data pattern and you get the difference, then you can see via the discrepancies why your model doesn't fit. And that will cause you then to figure out how to change your model to be more reflective of what the data want. Okay, with me so far? So then if we go across, let's look at this one right here that I've highlighted. This is items 3 and 6. The loading for 6 times the covariance between the factors, because they're on different factors, times the loading for 3. So this is saying that the only reason 2 items from different factors are related is because their factors are correlated. That's why they're related. That has the potential to be wrong. So this is the model predicted pattern. That's really what we're after here. We're not really predicting y. If we are, we're doing kind of a dissatisfactory job, because we can have things like, well, how much of y's variance is due to the factor? But then it's like, well, what's the factor? I don't know what causes people to be higher or lower on the factor. So it's not really explanatory in the way that a typical regression model would be, where you know what x means for sure. So if you're like, Lisa, can you stop showing matrices and just like use some words? If you're thinking that right now, the next slide's for you. So what we're doing here is keeping track of data going into the equation and then results coming back out and the match between them. So the purpose of the item intercepts is to recreate the item means. The item means are unconditional. The intercepts are conditional on a factor score of 0 specifically. So that breaks the tie between items and people. The item mean is sample specific. The item intercept is not. This is specifically for an F score of 0, no matter where you are, who you are. So if each item gets its own intercept, most of the time the means will be perfectly predicted. I used to say always, but then I had to change it because I stumbled into a class of models, cross-leg panel models in particular, where I've seen these get screwed up even if each item had a different intercept. So the very most of the time, but there's certain exceptions to that I've stumbled into in longitudinal case. Likewise, the purpose of the error variance is to get back to the full item variance beyond the part that the factor is creating. So if each item gets its own error variance, then all the item variances are going to be perfectly reproduced, or very nearly so. So right now, we don't have room to be wrong yet. Right now, everything is going to be fine. Here's the big one, covariances. The purpose of the factor loading is to recreate the pattern of covariance across the items. And now we have the potential to be wrong if we have more than 3 items for a factor. Loadings and covariances. That's really the only thing that we have to keep track of in terms of parameters and how many we have and how many we could have. Do I do that? Okay. So this is a lot. How are we doing? Okay, what are we doing again? What's the point? Are we predicting y? Not really. What are we predicting instead? What are we recreating? The what?
The observed.
We're trying to recreate the observed item what? Means is 1. 2 more. Item variance and covariance. The big one is the covariance. That's what we're doing. We are recreating a matrix pattern. There are 2 different versions of the model that you will see, and both of them are useful for different reasons. Matrix, yes indeed, Zoomers. So the default is an unstandardized solution, which is scale specific. So I would have to know what scale y is measured on, what scale f is measured on, in order to know, like, is that loading good or bad, right? If the loading is 0.2, that could be stronger than 2, depending on what the standard deviation is of these variables. The original unstandardized solution is useful when you're trying to compare across samples. So if you're interested in whether your item is equally discriminating in a new sample as an old sample, or for this type of population versus that type, then we need the original values. These are going to recreate the item means and variance covariance matrix, and then again pointing out the asymmetry. The intercept and the loading are direct item parameters, but when it comes to E is not a parameter. It's variance across persons is the parameter. So putting it together then, we're saying the total variance of y is the loading squared times the variance of the factor that it measures, plus whatever is left over is error. So like, this part will get you so far into recapturing that variance, this just fills in the gap. So E variance just fills in whatever is needed. The standardized solution then is also provided, and then plus it's the keyword STDYX. They have a couple different kinds. And this is rescaled so that all the variable means are 0, all the variable item variances are 1, and all the factor variances are 1. So then this puts everything into a correlation scale, and the standardized versions of the loadings reproduce the item correlations instead. So the original loadings as regression slopes reproduce covariances, the standardized versions reproduce correlations. It's the same result, just in two different scales. This is much more useful if you are trying to decide which items are relatively best. You look at the standardized solution, because then all the items are on the same scale. And if I have a loading of 0.6, that's better than a loading of 0.4. Everything has been standardized. It's directly analogous to the idea of standardized slopes in regression. The rest of the solution, no one cares. Standardized intercept is not a thing that you need to worry about. However, standardized factor loading is. Standardized factor loading squared is treated as an effect size for how well that item is being measured, or that measures that trait. So people do report either standardized loadings as correlations of R or their squared versions as R square. I do not think that you can use the term explained variance for this, though. That might be a semantic distinction, but to me it's not. R square in this context is the proportion of variance that is due to the factor, attributable to the factor. But we don't know why some people are low on the factor and others are high, so it still hasn't really been explained. It's just attributable. In random effects models, it works the same way. We might talk about random intercept variance as saying this much is attributable to your cluster, but we don't know why yet. So I wouldn't say explained, I would just say this is attributable or due to. And that means the standardized error variance is whatever's left, proportion that not, due to not the factor instead. Okay. So then putting that context of two different solutions in terms of what the model is supposed to do, the unstandardized solution, if I have the covariance between 1 and 3, for instance, that are on the same factor, this is the pattern, this is how it gets created. If I have the correlation between them, I replace the unstandardized loadings with their standardized counterparts, and I replace the variance of the factor with 1. So when people talk about patterns, they usually look at this one because it's easier to keep track of. This is saying that the only reason that these items are related is because of the factor they have in common, and that's it. There's nothing else in the model that is currently contributing to their covariance, no error relationships, local independence. Items from different factors then, same principle. It's unstandardized are the loadings that for each of the items plus the covariance of the factor. So they don't measure the same factor. The only reason they're related is because the factors are related. In the standardized solution, we switch the covariance between the factors to correlation, and we switch the standardized loadings. So the variances then should be reproduced, as I noted before. All right, so there's my picture. How are we doing? Abstract. I know it's very abstract. I do have an example, though, I promise. It's like a 27-page handout. It will take a while to go through, but I'll put that up next week after I make some more tweaks. Okay, so let's talk about how imaginary things can have means, variances, and covariances, shall we? Because that sounds like a lot of magic to me. We make them up, is the short answer. I know that's a little anticlimactic, but it's true. So we need to talk about something called model identification, which has two different ideas as part of it. Part one is that every imaginary latent factor needs to have a scale. It needs to have a mean and a variance. This is necessary but not sufficient. After that, we have to make sure that the model itself is estimable, that we have enough information to estimate all of those parameters. So the number of means becomes the number of intercepts. We're good there. Number of item variances becomes the number of error variances. Good there. Covariances versus factor loadings. This is the problem. This is what you need to pay attention to. You need to have a ratio that is greater than or equal to 1. You have to have fewer factor loadings than covariances in order for the model to be testable. If you have the same number, it's not testable, but it's estimable. So those are the conditions. We will get into each of these. So this means that one. In path models, it also means that you can't have a direct relationship between two things two different direct relationships between two variables. So don't try to do the models where there's like two boxes and then there's arrows that go like this. Those things are technically possible under very specific constraints, but they don't make sense. I mean, come on, right? You have one correlation and you're going to get two arrows out of it? No, don't try to do that. Okay, so here's how we're going to make up a scale. There's two different strategies that people use. One is to treat the factor as a standardized variable or as a z-score. So I would just say, you know what? Factor variance is 1. Done. I said it. I'm going to tell the software about it. It's fixed. So we would say the variance is constrained to 1, fixed to 1, set to 1. I will use the term nailed down quite a bit as this idea. Like you're pitching a tent and you have the, the spoke end. Okay, the tent's not going anywhere. I've nailed it down. You can't have a tent stay up unless at least one of the poles is nailed down first, right? That's the same thing helps here. So if you do it this way, then you get to estimate all the factor loadings. If you do it this way, then your slope tells you the change in y for a 1 standard deviation change in the factor, which is convenient. The only problem is that you can't do it this way if this factor is to become an outcome. So once you get into the world of SEM, where you have multiple factors at the same time, and maybe one's predicting the other, then if this factor is being predicted, the variance of it needs to be free to become some other number after being predicted. It needs to be estimable. It can't be nailed down anymore. I've seen that cause estimation problems. So the alternative, and what is the default in every software package, by the way, is this version. Your textbook calls this the marker item. Instead of fixing the factor variance to 1, you fix one of the loadings to 1 arbitrarily. It does not matter which one it is, so long as it has a relationship with the factor. The default in all software is the first one is fixed at 1. You don't have to do it that way. There's nothing wrong with picking 2 or 3, but it really doesn't matter. If you do it this way, then what happens is that the part of the marker item's variance that the model thinks is due to the factor becomes the number that the factor variance is. Let me say that again because it's convoluted. If you do it this way, the part of the item's variance that is due to the factor, that number, whatever it is, becomes the factor variance. So as an example, if I have a standardized loading and the item variance was 16, then I take that loading and square it, so that's like the proportion of variance that's due to the factor, times the total amount of variance, that gives me this number. So then on your output, the factor variance would magically be 12.96. The only way you would run into problems doing it this way is if you pick an item that does not have a relationship to the factor. I have seen that happen to one student. Her model blew up. She got error messages instead of output, and I looked at the code and I was like, there's nothing wrong with this. Why is this not cooperating? And on a hunch, I'm like, put the loading on 3. Pfft, worked. Turned out, item 1 was not correlated with the factor. So what happens if this is actually wanting to be 0 in terms of the correlation, it's trying to pass up 0 variance to become the factor variance. And you can't have a factor with 0 variance. It doesn't work. That's called a constant, not a variable. So that's the only case in which it makes a difference, is if you pick the wrong item because it doesn't load at all. Does this seem arbitrary to you? How you give the factor a scale? I think it seems arbitrary. Zach, question?
So the factor variance depends on what item you pick?
Yep.
Okay.
It does. So if I picked an item that had a standardized loading of 0.7, then it would be a smaller number. 0.7 squared times 16, whatever that is. Don't make me do math in front of you. Yeah, it could be 1. Question, how often do items have no correlation with the factor? Depends on how crappy your scale is. I can't answer that. I would say the newer the measure or the more difficult or ambiguous the construct, the more that is likely. Or the longer your item and the harder it is to understand, potentially. There's many ways to get a bad item. But you won't know unless you stare at the correlation matrix in the first place, right? If you have an item that's not correlated with anything else, that's not good. That means it's going to have a very low loading, maybe 0. What happens if one of my loadings goes negative? Can that happen? Could my slope be estimated as -2? Yeah. What does it mean then? Inverse relationship. As the factor goes up, y goes down. Unless you forgot to reverse code, that is a bad item. It is behaving the opposite way that you want. So this is completely arbitrary. What if I decide that I want to have a factor variance of 15? Can I pick 15 instead of 1? Is anyone going to yell at me about that? What do you think? Can I do it? How about 27? Can I do that? How about 0? Can I do that? No, that won't work. That's the only one that you can't pick. So this is completely arbitrary, but it's not wrong because, again, these are imaginary. And the way that I describe this, I've got 2 analogies I can give you, both from my real life. One is from taking, at the time, the GRE had an analytic section instead of a writing section. And it was filled with logic problems like, if Bob is twice as old as Greg, and Beth is 3 times as old as this, but this person's 2 years younger than this, then how old are they? You need to know one person's age, and then you can work through the rest of it, right? This is the same way. You need to know one thing, and then you can work through the rest of the math to figure out what all the other pieces would be. The other example I can give you, story time. Do we need a story? I kind of feel like we need a story. It's a good story, maybe. When I was in college, I waited tables at a restaurant called Grisanti's in Lincoln, Nebraska, which is very much like an Olive Garden, except we had loaves of bread instead of breadsticks. And as they do at the Olive Garden, when it's your birthday, you get a free ice cream sundae with a little like candy stick in it to look like a candle, and the wait staff is supposed to sing to you. And I had to sing. So what we had to do is get our sundae and just start walking around the restaurant looking for anyone else who works there to come sing. And it was one of those deals where some people would just run and hide, like they just wouldn't participate. But then when they needed singers, we would remember and not go. And so they'd have to do it themselves. So it's like a team thing. Like none of us wanted to sing, but we all had to do it. But the key was that whoever started singing first could pick the key. So I always started singing first so I could pick something nice and low. And the song was, me, 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 happy birthday to you, hey, happy birthday to you, ho, happy birthday, dear so-and-so. And then people of the opposite gender had to lean in and say, baby, happy birthday to you. And then we'd all clap. Okay, and then we'd run away because everyone was really embarrassed. No matter where I start the song, if someone else got there first and starts singing, and they go, me, 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 I'm not going to sound good, but it's still the same song, and we can figure out how to go up and down from there. So I think of this as like picking a key. You pick a key to play your song in, and then the rest of the notes just rearrange themselves accordingly. Like this is up 2 steps, this is up a half step, and so on. So no one questions that, right, in music. Like no one says, why did you pick C? That's the wrong key. It's only the wrong key if you can't handle C. So it's just these parameters will rearrange themselves relative to whatever you've nailed down with your tent pole. That's why it doesn't really matter. And there's not a choice that is more right than the other with these exceptions. This variance needs to be estimated if this factor is to be predicted, and this loading needs to be related to the factor for this system to work. Other than that, you're good to go. That makes sense? Fair enough. Guess what happens to the standardized solution if you choose this way versus that way? Do you think it matters in the standardized solution? This is a yes-no question. Got 1 vote for no. Can I count you as a no? You're shaking your head? Okay. 2 votes for no.
Depends what you mean by doesn't matter, because I think there would be relative differences, but in the grand scheme of things, it wouldn't matter.
The question is, does the standardized solution change if you identify your model this way versus that way? Standardized solution, all variable means are now 0, all variable variances are now 1, and the factor variance is 1. It does not matter. Standardized solution is on its own separate scale. So your conclusions about which items are relatively better will not change. So like if this is 1 and item 2 is a better item, then its loading might be 1.3. And if I decide to make item 2 the marker and now it's the 1, then this loading might be 0.7 instead. Like it's all just relative shifts relative to whatever you've set as the 1. And this number, by the way, this loading, this could be 10, this could be 27, this could be whatever too. It just needs to be nailed down. So variance of 1 or item loading of 1 for that. So now our pretend imaginary variable has a scale, has a variance, but it also needs a mean. And we have the same 2 arbitrary decisions to make for that. We can either stick with this idea that the factor has a z-score scaling, and we fix the factor mean to 0. So now the mean is 0, the standard deviation is 1. That's nice and convenient for interpreting the intercepts because they become the means specifically. Alternatively, you can stick with this idea that item 1 is like the anchor point for the model, and you estimate the factor mean instead, and it becomes the mean of item 1 because you fix its intercept to 0. So in this bottom picture then, if I did both of these, where the factor variance is due to the part of y that is due to the factor, and its intercept is 0, then this factor completely has the scale of y1. That's what will happen. It will have y1's mean, and it will have the variance of y1 that is due to the factor. So yeah, your factor mean would differ if you picked another item to use as the marker. Still arbitrary, but everything is still going to arrange itself. Putting it all together then, these are your 4 choices. You can have any of these combinations. In this class, I'm going to ask you to do top left, standardized factor. That makes the interpretation of the slopes easier. It makes the intercepts become the item means rather than some weird value. However, top right picture is the default in M+ and in Lavon. First item fixed to 1, but the factor mean fixed to 0. So it's a combination of the 2. The others are logically possible, but not as commonly used. Okay, how are we doing? So we're predicting item means, variances, and covariances. In order to do it, all of our factors have to have a scale. Either we arbitrarily say this number, or we let one of our variables give it a scale. Then part 2 is making sure that the model is estimable. And this is the part that would guide the question, how many items do I need? And the answer at the end of this, as I'm going to tell you, is at least 5. And here's why. So we're estimating different parameters for the measurement model, the intercepts of the items, their factor loadings, and their error variances. So measurement model covers how the items relate to the traits they measure. Structural model parameters are factor things then, factor means, factor variances, and covariances. So we are heading towards evaluating how well our model fits as the difference between the model recreated and data observed item variance covariance matrix. How many possible parameters can we estimate, and do we have enough data by which to do it? The question is degrees of freedom is what we call this, and it has nothing to do with people. Okay? Like in every other stats class, degrees of freedom is based on sample size somehow. It is not. It has nothing to do with people. So these formulas are not based on number of people. They're based on number of variables. So I've got V here for the number of items. Total degrees of freedom number of possible things I can estimate is the number of items times the number of items plus 1 divided by 2. That part gets me the number of variances and covariances specifically. Add plus v again to get the number of means. So if I have 4 items, I throw that into the formula, and I have 14 things I can estimate. Here's the list of the 6 different types of things I might want to estimate, at least for now. We don't have error covariances yet, but that would be added later. And I can have 14. So then we have to make sure that our model is identified, is solvable, because it has not negative degrees of freedom. So you can think of this as data input minus model output, or number of possible parameters based on the number of variables minus the number estimated. So number left over is degrees of freedom. Number of things you could have estimated but did not, relative to how much data you have. So here's what happens if you have 2. And a new vocabulary word for you, under-identified. Synonyms include not identified or broken. This model is not solvable. And Bayes can't fix it. Ha ha. Yeah, thank you. A few of you got that joke. Count up what we need to do here. So if I have 2 variables, how many pieces of information am I starting with? I've got their 2 means, their 2 variances, and their 1 covariance. That's 5. Okay, that's the maximum number of parameters I can estimate. So one way of identifying the model would say, I'm going to fix the factor variance to 1. I'm going to fix the factor mean to 0. That would mean I have no structural parameters and everything is a measurement parameter. So because I have 2 items, I might want 2 loadings. Each gets an intercept, each gets an error variance. 5 minus 6 is minus 1. Degrees of freedom are negative, meaning you are overdrawn in your information bank account. This model will not work. The reason is, think of it like with this kind of equation. If I have x plus y equals 7, solve it. Here's at least 3 versions of it that would work, and this is the problem. We don't have enough information. But what we could do is put constraints on it to reduce the number of things we're trying to estimate. The most common solution would be to force these 2 loadings to be equal in the software. You tell it, make these 2 the same number and go figure out what that number is. That's called a constraint. Then we lost one of the item loadings and degrees of freedom are 0. Then we can do it. However, practically speaking, what are we saying about our items if we fix both of these loadings to be equal? Like, what does that mean conceptually? Equally good, equally discriminating. Yeah. So in this case, literally what you are doing is taking the correlation between these 2 items, drawing a circle around it, and giving it a name. There's no point to doing that. So, as I have a side note here, some of the assumptions required to calculate 2-item reliability or 2-score reliability in classical test theory are because of under-identification right here. So under-identified means you are trying to do too much. You don't have the data. Just identified is another vocabulary word. That's what happens if you have 3 items. So let's go through the possibilities here. Either I have 3 item loadings and no factor variances, or I choose one of my items to be the marker, so I only have to estimate 2, but then I have to estimate the factor variance instead. Likewise, I could have 1 intercept per item and no factor means, or I could have 2 intercepts, fix one of them to 0, and estimate the factor mean instead, and it will become that item's mean. Either way, I could have 3 error variances. Now, in terms of possible information going in, 3 means, 3 variances, 3 covariances. What's coming back out? 3 loadings, 3 intercepts, 3 variances, 0. So degrees of freedom 0 means just identified. Means it is just reproducing the data directly. You cannot be wrong. Now, that doesn't necessarily seem like a bad thing, that you can't be wrong, but from a hypothesis falsification point of view, it is, because you can't be right either. This is just a description of the data. It's a reparameterization of the correlation matrix with no savings. And in your textbook, they have an example of how it works out to this, so I thought I'd throw this in here. So let's say that we're working with standardized solution to make it a little bit straightforward. This is the correlation matrix among the items. I have loadings A, B, and C that I'm trying to estimate to fit these correlations. So if I know that the correlation between the first two items here is 0.595, the way the model would recreate that is whatever the A loading is times whatever the B loading is, because the factor of variance is 1 in the standardized solution. Okay, so I know AB has to be that number. Following the same logic, the correlation between 1 and 3 has to be due to A and C, and then BC covers 2 and 3. And then if I decide to solve for B and solve for C, then I can figure out what A is and work backwards and get the rest of them. So it's perfectly solvable, but you're not going to be doing yourself any favor because you actually can't answer the question empirically, do these three items measure the same thing? There's no room to be wrong, so you can't test it. So over-identified is where we want to be. That means we have made a testable model by estimating fewer parameters than we possibly could. We've got room to be wrong. Where we have room to be wrong at, though, is the covariances. That's it. So if I have 4 items, let's say that I have a standardized factor again. So variance is 1, mean is 0. I don't need to estimate those. Then I've spent 12 degrees of freedom to estimate this model. 1 loading, 1 intercept, 1 error variance per item. 14 pieces of data going in, because this set of 4 items has 4 means, 4 variances, and 6 covariances. So now I have 2 left over. I have room to be wrong. But where I'm going to be wrong at is 4 loadings versus 6 covariances. That's where the room is. The means are fine, the variances are fine. It's that the 4 loadings are trying to reproduce 6 covariances. That's where we have room to be wrong. Sometimes, though, you can do everything right and still be wrong. And this is called empirical under-identification. It's not your fault, it's your data. Let's say that you have a 2-factor model, like this, where you have each factor being measured by 2 items. Each of these factors I would call is locally under-identified. Like if you just had the 2 by itself, that's not enough. And this 2 by itself would not be enough. The only way that this works is if there is a covariance between the factors. Then this works, because how many degrees of freedom would you have then? Let's count them up. How many intercepts am I estimating in this little picture right here? How many item intercepts? How many little mu things do you see? 4. Okay, how many error variances? 4. How many loadings? 4. Do I need to worry about the factor variance if it's fixed to 1? Or the factor mean if it's fixed to 0? So I've spent 12. I have 2 left. This is going to be one of them then. So now I'm down to 1 degree of freedom. That's why this works, because the model as a whole is over-identified. But if this covariance is 0, then it's like you're splitting this into separate models, and each of these is not identified on its own. So this could work so long as you're sure your factors are related. And also in this situation, this model is now unidentified. If one of your indicators is not related to the trait, then it's functionally just like having 2. So that leads me to my advice: have 5. Because you have room for 1 to crap out on you, and you still have 4 left so that your model is identified and testable. From a reliability standpoint, though, do you think 5 is enough? Would you want to take a life-altering test that had 5 items on it? No. No. So goals of measurement depend on what you're trying to do. In terms of having your model be identified and testable, 5 is good. In terms of having a good measure of individual differences in your trait, 5 is probably not enough, unless they're really, really good items. There are folks who actively encourage people to only have 3. The analogy is used of a 3-legged stool. If you have 4 legs, it gets wobbly. 3 legs makes it balanced, is the analogy. Don't listen to that. You don't want to be in a situation where you can't defend yourself, because this model is not testable. It is a recreation of the data that is guaranteed to be perfect, even if this factor is not actually being measured by these 3 things. The model can't tell you that. So 3 is not a good idea. Okay, how are we doing? Hanging in there? Anything that you want to ask about or you're thinking about in terms of your own scales? Is anybody going to be in this situation when they analyze their data?
I have a question out of my curiosity.
Hmm?
Can we go back to the 3-item slide?
Which one?
3-item slide.
3 items. That one.
What if I run 3 versions of that, and each time I set lambda 1, 1, and 2, 1 to be the same, and 2, 1, 2, 1 to be the same, and 1, 1, 2, 1 to be the same?
So the question was, what if I constrain these loadings to be equal?
Yeah.
Or
3
2 of them
times,
maybe?
Yeah, 2 of them.
At least 2 of them? Well, then in terms of our tally, we cross out one of the loadings, if you constrain 2 to be the same number, and now we have 1 degree of freedom.
Yeah, so in that case, if I run it 3 different times with 3 different type of constraints, will that be able to tell me something? Compared
Then it is testable, but just barely, like 1 degree of freedom left over. And yeah, that's what you would have to do in that case. However, I think the pattern of loadings that you get back, even though the model's not testable, would guide you as to whether that's a good idea or not, right? If they're very, very different, I wouldn't try to do that, because then it's going to show up as bad fit, because the pattern of correlation they generate when you force them to be the same will not be a good match for what the data actually wants them to be. 5 items for each factor. Question from the Zoomers, yes. That way you can have 1 go bad and still have 4 left. Zach, go for it.
If you add a correlated error, does that add another, like, well, yeah, what does that do to the degrees of freedom?
It adds to the things you are trying to estimate. It does not change the data going in to estimate them with. So in this model, if I have 3 separate loadings, I'm busted. I don't have any room. I can't add an error correlation. In this model, how many could I possibly add? 2. Then I'd be busted. 0. My son, when he played Monopoly when he was 3 or 4, he would say that he went bald instead of broke. So that's what I keep thinking of. Like, Daddy went bald. I got all his money. Like, okay, I see what you mean there. So yeah, you don't want to be bald. Then you can only have 2 error covariances here. And those, by the way, is a 2-headed arrow between the e's, is what that would look like in the diagram, and it would add to the number of things to be estimated in the measurement model. However, I don't think it's a great idea to add 2 error covariances here, because these are already supposed to be measuring something in common. So if you need 2 extra relationships, that means that they're probably not as much in common as you think. All right, other questions or thoughts? Okay, then a few minutes on this, I think. Yeah, we're almost done. Really, I'm like out of slides. It's amazing. So here's what happens if you get your errors wrong, what you're saying. The other kind of measurement model that you will see is what's known as a formative or emergent factor model, as opposed to what we have this semester, which is reflective. And this is a very different type of theoretical statement. In our view, we have this imaginary latent trait that we think came first, and what you're standing on this trait is the reason why you answer your questions the way you do. It's backwards. They think the answers came first, and the sum total of the answers somehow combines to make a whole new thing. That's imaginary. That's a formative measurement model. In what we're doing, if the items are not correlated, it's game over, because there's no way that your pattern can be recreated by a factor if there is no pattern to be recreated. Your items have to be correlated. In a formative model, they do not. And our models are identified even without adding in extra information, whereas this one is not. So here's a picture from your textbook as an example. This is 5 indicators that are going, the arrows are going from the boxes to the circle. It's not very visible, but that little thing right there. So they're thinking that these things create this new latent variable that's called chronic life stress. And note what's at the bottom of the boxes. What do these little things mean? 2-headed arrows connecting all the boxes. Those are covariances. So this model says all 5 of these are related and they combine to make this whole nother separate thing. It's not identified. If you count it up, we have 4 loadings, 1 error variance, so he's doing it a little bit different way. By the way, factor variance left over is called a disturbance, which is sort of funny. They can't say error variance, like there's a disturbance in the force. There's 10 item correlations down here. Each of these items needs a variance and each of them needs a mean. So we're at -5 for our degrees of freedom. Not going to work. This model down here is identified. I now have 3 formative indicators that create this thing called chronic life stress that in turn tells you how you're going to answer 4 and 5. So the top part of this is our standard reflective model. The bottom part is formative. And now if you tally up the list of things you're trying to estimate, it is identified. So examples of when you might think of a construct this way. Adverse life events. They're scales that, like, number of crappy things that have happened to you either as a child or a grown-up. You know, did your parents get divorced? Did you have a tornado? Did you have chronic health problems? Were you abused? All this stuff, right? If you wanted to use those kinds of items as reflective indicators, what kind of trait would have created all of those events in common? So I listened to the Quantitude podcast. Some friends of mine talk about this kind of stuff, and I'm borrowing Patrick's example. He did this in grad school, apparently, and one of his colleagues named the factor the evil eye. Like there's like you're cursed. The latent variable is you're cursed, and it's going to make you get your parents have a divorce, be abused, go through a tornado, be poor. Like there's another one, right? All these adverse events. Like, can you think of any trait that causes all that stuff to happen to you that's so disparate? That's a stretch. But is it true that the number of shitty things that have happened to you probably matters, like in the aggregate? That's the idea. Like, so these are the kinds of indicators of like what things cause stress, like money, relationships, health, other kinds of resources, right? These are not necessarily correlated, but they could combine to create this new thing. That's the idea. Socioeconomic status is another type of formative type of measurement model. Those indicators are not necessarily caused by something. Your parents' education level, your zip code, your job prestige, those are not caused by something in common. As an example of the bottom one here, one that I saw that I thought was useful was housing prices. What makes a house valuable? Location, size, number of bedrooms, number of bathrooms, how new it is, whether you have a fireplace, I don't know, like just features, right? So if you think of those things as formative indicators that come together to create this latent construct of house value, then how could you measure that with reflective indicators? Well, that's what appraisers do, right? So if I have 3 people come to my house and tell me how much they think it's worth, right? My house is the thing that is causing them to answer the questions the way they do. That part's reflective. What causes my house to be valuable, though, is other indicators behind me. So there are situations in which you can pull this off in a reasonable way, but there is no way by which to say this works as a construct without bringing in external variables. Because the only way you know what this thing is that they create is for it to be related to other stuff. So there has to be kind of a prediction element besides just a measurement focus, and that's where it breaks down. So we're not going to do formative measurement models. We're going to stick with reflective because they're not separately identified. There's a whole big literature on it, though. And if you're interested, I can give you some additional sources. I think there's one on your reading list about this, a recent paper. Okay, so we made it. Look, summary slide. CFA is a linear model. It's a regression model with a pretend imaginary variable. We don't actually try to predict why, though. What we care about is the pattern of association across the items and whether our model is consistent in terms of what it predicts with the data. We need 4 items for that single factor to be testable. So this framework offers advantages over adding shit up because you can actually test the dimensionality, that they're all adding, what's being added together measures the same thing. You get indices of difficulty and discrimination via the intercepts and factor loadings respectively that are not sample specific. The intercept is specifically for a factor score of 0. And that means that you don't necessarily have to give everybody the same items. If you're trying to measure a trait in different samples and certain items are not relevant for that one of the samples, don't include it. There's nothing wrong with that. Because you have this trait that is separate from the sum of the items, you don't have to have the same items. And that's the basis of things like vertical equating, where you deliberately make a test harder over time so you can stay sensitive, or even computer adaptive testing. That's the magic that makes that possible. All right, 144, we made it. You're like, no. No reaction? Really? You're not happy class is done? Yay. Maybe I'll take that as a compliment. You don't want class to be over.
There's another one.
There is another one, yeah, I know. Maybe that's it. Everyone's in the second class too, and you're like, I gotta sit here for 2 more hours, Lisa. You chose it, and I gotta sit here too, to be fair. So, all right then. Let me know if you need anything. You can be working on your formative assessments. That's due Monday. You can get started on homework 1, which is due after that. Have good weekends. Bye for now. Bye, Zoomers.